Hey, Jeff. Uh,
Hey, Daniel.
Thanks for coming to my show. Jeff Breeding. I know you as Jeff Breeding, but you come up as Jeff Breeding-Allison.
Right. Yeah. When I got married, we hyphenated our names together.
Wow, is that a... Can't see myself. Never thought of taking a wife's name. Is that a thing a lot of people do? Just out of curiosity.
Some people do it. I know another mathematician who did it, David Zurich Brown. He's at Emory. And yeah, I mean, it's not that common, but some people do it. I'm not the first.
Well, I'm not super attached to Ruben, but you know, I don't know. But I'm a man though. So anyway, okay. Here's why you're on my show. It's not to discuss that. It's because you're a mathematician. I'm a mathematician. We're both out of academia, and we're still in the fight.
Right.
Now, did you see this movie Sicario? Just out of
yeah, I think I saw it. As
Benicio del Toro.
Yeah.
And there's a guy who sees him, he recognizes him, and he's like, he praises him for still being in the fight. That's what I feel like. And you do number theory, and I used to, number theory was my first love in math. And I got plenty of questions about that and plenty of questions about your career path. And maybe we'll just...
Really? Number theory was your first love in math? We met at Park City Mathematics Institute in the summer of 2009. They had a session on the arithmetic of L functions. And that was after my third year in grad school, and you were just finishing Johns Hopkins, right?
Right. I mean, okay, but it goes back further than that, you know. Okay, I mean, maybe we've never discussed this, even though we've been friends since then. You know, my first exposure to some real mathematics was at this thing called the Promise program at Boston University. So when I was 16, I was shown this world of number theory, of, you know, questions about primes and the Gaussian integers and quadratic reciprocity, things like that. So that was the thing that told me that there was this world of math out there. And I wanted to do number theory, or so I thought. I mean, I entered college with this big ambitious plan that I would, by the time I graduated from college, I wanted to understand the proof of Fermat's last theorem. I don't know if I ever mentioned that to you. And of course that did not happen. That things went astray. I mean, I was interested in some other stuff, or whatever courses were being offered, and I liked certain professors and followed their work. And so ultimately I went in a very different direction. I didn't do number theory. I had some number theory. I guess when I went 2009 at the end, I had taken a course in algebraic number theory, and I was encouraged by that professor to apply for that Park City thing. So I was still interested, and I wanted to, I was interested in the Birch and Swinnerton Dyer conjecture, but but I was relatively new. That was really for grad students, and I had only a little bit of background. And when they started talking about, I didn't even know what projective modules and motives and Euler systems, they lost me completely. I didn't know what they were talking about. And I didn't look back until way later. But I'm still into, but you know, I'd like to keep tabs on mathematics, on different things. And now I guess I came back my first year as a postdoc, just looking for different things. I started reading my old books again, now with a new perspective, now that I'm a trained mathematician.
Your old books again. Which books were you reading?
I got back into this book by Anthony Knapp. Is it Knapp or Knapp? Knapp, but on elliptic curves. And now I can, you know, read that book, and now I can see what I think is important, what isn't important, in a way that I didn't used to. And so I am full of questions for number theorists, because now I come from a different way, but a different path, but I want to know all sorts of things. I still don't understand this proof of Fermat's last theorem. And I know that's the kind of thing that you do, right?
It is the kind of thing that I do, but there's a lot of really great results in that proof. And my work was kind of concerned in looking at kind of the next step for this Taniyama-Shimura conjecture. That's kind of treated as like a degree 1 case, what I eventually studied in looking at what's called the Paramodular Conjecture.
Okay, well, I've never heard of that. So, okay, how about we start like this? Because I think this worked really well with my friend Connor. How about, why don't you try to, can you explain what you do, your work in number theory, say first to a lay audience? How would you explain it if you tried to explain it to a lay audience? And then we'll just go more detailed from there. I have questions and see what I can get out of you.
Sure. So I want to understand at kind of a deep level the structure of number fields. And I get to this understanding by doing various computations with things that come out of these number fields.
Just say what's a number field?
So a number field, an example is the rational numbers, so integers over integers, or any kind of extensions of those. You can take in the rational numbers and then join the square root of 2, for example, and get a larger number field. You can look at the real numbers, that's another number field. C, the complex numbers, is another number field. I want to understand these things at kind of a deep level. What is their structure, and how do we kind of relate different elements in those? And a lot of,
I guess I thought number field meant algebraic extensions of the rationals, but I don't know what terminology.
Yeah, so extensions of the rational numbers, that's kind of the base field in number theory. And then you look at various ways of constructing new number fields out of that. And that could be by adjoining solutions of a polynomial equation, or you can complete it with respect to some way that you measure distances between numbers. For example, for the real numbers, you get that by adding kind of completing the field. I'll say what that means in a second. By looking at the distance between two numbers, that's basically the normal way you measure distance, just the length between the lines.
Yeah, well, look, I know this is the thing I teach in analysis. It's just measurements. If you were able to take a sequence of measurements with ever more precise rulers,
right?
That's what we call a real number. But you're looking more like at the algebraic side of things.
Yeah. So the real numbers is just one way of completing the rational numbers with respect to the way you're measuring distance. For the other ways, it relies on the fact that we have these special integers called prime numbers. And there's this unique factorization theorem that says that every integer can be factored uniquely as a product of primes raised to some power with a plus or minus 1 at the beginning if you're looking at non-zero ones, positive and negative. And you can extend that to looking at prime factors of rational numbers. So rational number, you have an integer over an integer. You can factor out all the primes there and basically get one prime times some other rational number where the numerator and denominator don't have any more of that prime factor p that you pull out.
Mm-hmm.
And one way you can measure the distance between two numbers is how common this prime factor is in the difference. So if you look at the difference between two rational numbers, that makes another rational number. You pull p raised to some power out, as many powers of this prime p as you can. And then you take that as kind of a way of measuring distance, where if there's a very large prime factor, p raised to some large number, then you say that those numbers are very close together.
Right, which is, I guess, different from the ordinary, 1 plus 3 to the 5th is very close to 1.
Right.
In the three-adic sense is what you're saying.
Yeah, so you measure closeness based off of prime factors, not kind of the length with these rulers or whatever. And that gives another way of measuring distance with the rational numbers. And there are some theorems that say that these are basically the only ways of measuring the distance between two rational numbers, being somewhat loose with the language, but that's essentially what it is using basically this measure of distance and factoring out these primes p. So then you look at completions of the rational numbers, completing with respect to the normal distance that you're used to, you get the real numbers, completing with respect to this other distance of factoring out primes p for all the primes that you like, you get these things called p-adic numbers. And so you can construct things in a much nicer way in the p-adic setting because of the structure that they have in relation to prime numbers.
Yes, so there are all these different completions. What I want to hear about is a problem. What where's the problem? So far you talked about these
Right.
constructions.
Yeah. So I became interested in a few problems in number theory, and my research falls under this thing called the Langlands program that involves connecting these seemingly distinct areas of number theory together. You have representation theory, where you try to understand how groups defined over these number fields, how they act on vector spaces, and basically find what are the irreducible representations and what do those look like, and understand all the kind of ways you can act on vector spaces with groups defined over these number fields. So that's what I focused mostly on, kind of the first part of my graduate studies in mathematics. The other part of the Langlands program is on kind of a harmonic analysis, modular form kind of thing, where there you can find some kind of more easily stated problems, like ways of counting the number. So you can find out the number of ways of counting, how you can write, say 5 as the sum of 4 squares, or 8 as the sum of 6 squares, and things like that. Those are all encoded in these special functions called modular forms. And then there's another aspect for the Langlands program called algebraic geometry, where you look at these abelian varieties, and they have some points defined over finite fields, sometimes not.
I think
And you try to like
we've
relate
lost
all
some
these
people.
objects.
Oh,
Yeah.
Okay. I mean, probably lost some people about the representations of groups, and we didn't say what a modular form is, but that will, I mean, maybe we just have to, maybe there's no point in saying everything, but I don't know, you say abelian variety, something's got to be maybe explained here a little bit.
Right. So the algebraic geometry side are basically these curves, for example, that have some structure to them, where you can add 2 points and you get another point on this curve. So they satisfy these operations in a nice way that you have what's normally called a group in algebra, where you have some binary operation of combining 2 elements. So these are 2 points on this curve, and it produces another one. There's a special point called an identity element, or if you add that point to any other point, you get that same point back again. And you have these kind of inverses to things, where you take a point on the curve, there's some other point where if you add them together, you get this identity point. So it has this kind of algebraic structure where you have some addition law.
Okay, so those are the objects that you study.
Right.
And what is the question? What is the question that you're trying to answer?
The question is, what is the relationship between the objects in these 3 different areas, if there is one? Is there some representation that you can attach to a modular form? Is there some modular form you can attach to something from algebraic geometry?
And Langlands said there should be, so you're going to look for it.
Yes.
I mean, okay, the way I'm inclined to look at it is, you could take even the simplest case, I believe, of what you're saying is just like, what can we say about the points, rational points on elliptic curves, or even their points over finite fields, or whatever? You can look at that equation of a curve and reduce it mod p, and you'll get some finite number of solutions for every prime p. And something about those numbers is very special. And it seems like so that the object you form out of these numbers, its L series, actually has all these other properties. These
Right.
this sequence of numbers that are totally unexpected.
Yeah, so each of these 3 areas, they say something about number theory, and there's some results that you understand more of the structure of numbers, or something related to structure of numbers, not to get into too much detail. And they don't seem to be related because you're computing these things in a different way. But it turns out that you're actually describing the same thing with these special functions, like you mentioned, these L functions that you attach to an elliptic curve, to a modular form, and to some kind of special representation. It turns out you can give some criteria to say that these L functions are kind of like a dictionary to go from one part to another, because of the information that they encode. Even though it's completely different, it turns out to be, it gives you the same thing.
Have you seen on the homepage of my channel, I put an image of this very ancient tablet. Did you see this?
I haven't seen it. Should I take a look?
Have you ever heard of this thing, the Plimpton 322 tablet?
Then sounds familiar, but remind me.
This is the most incredible object. I mean, I think once you know what this object is, it has to change your whole view of history and everything else, because I guess in the early 20th century, maybe even the late 19th century, they dug up in Iraq a whole bunch of clay tablets with very ancient cuneiform writing on them. And some wealthy guy, George Plimpton, just purchased a bunch of them and took them back and kept them in his collection. When he died, he gave them to Columbia University. And at some point, I mean, a lot of them are just, people look at them, they're tables. They seem that we can read Akkadian now, and they say, like, here were the grain yields from all the different farms or something. But one of them it's just tables of numbers. It's rows and rows of numbers. And what are they? They're written in base 60. They're Pythagorean triples, okay? And large, not trivial ones either, okay? And this thing is almost 4,000 years old. It's from the time of Hammurabi, they think. So that means that they were figuring out all these rational points on a curve,
Right.
in this case, a conic on the circle. Now, there's some speculation as to whether they really appreciated that they knew Pythagorean theorem, the so-called Pythagorean theorem, at least 1,200 years before Pythagoras. And not only that, but probably appreciated also issues about irrationality and why they wanted a rational trig table, whatever, we don't know. Or if they were just making a quadratic table and this was a school exercise. There's some speculation there. But look at these people 4,000 years ago, they knew how to do this. And then the Bronze Age collapsed and it was totally forgotten, had to be rediscovered by people like Archimedes and then later Diophantus. And then the Roman Empire fell, lost again, kept alive by some Muslims just copied Greek texts. And finally, by the Renaissance, it made its way back to Europe. And Pierre de Fermat has a copy of Diophantus's text from 250 AD, and he recreates the same method, right, to find rational solutions to these equations. And if you just go 1 degree higher, you just go to that problem was solved in antiquity, and even more than antiquity, like really archaic. You go 1 degree higher to cubics, and you're talking about a modern problem. How do you produce that same table? Are there infinitely many points?
Right.
What can you say about it? And it turns out, seems to have a lot to do with these issues of these modular forms that we.
Yes. So let's talk about Fermat's last theorem. So this is a problem that was solved using these relationships that were identified between representations of a certain kind, modular forms, and elliptic curves, these things from algebraic geometry. And this example that you gave about on this clay tablet, they have Pythagorean triples. So what are those? So everyone knows Pythagorean's theorem that if you have a right triangle where you have one side of length x and another side of length y, and the hypotenuse, the long side opposite the right angle, is length z, then x squared plus y squared is equal to z squared, right? So
once on a first date, the girl asked me to show her some mathematics, and I proved that theorem. It's the first theorem. First theorem I think people ever prove, but continue.
Right. First theorem for the date, or were there multiple theorems?
No. I mean, she really insisted. She's like, okay, really tell me something. This is like the first thing, but just
okay.
I didn't volunteer. I didn't say I can show you. No, continue.
Okay. All right, so that's the Pythagorean equation, x squared plus y squared is equal to z squared, is that it has this connection to geometry, right?
Shortcut.
So if you want a Pythagorean triple, those are 3 integers that satisfy this equation. So for example, the 3, 4, 5 triangle, 3 squared plus 4 squared equals 5 squared. Another example would be, I guess, 5, 12, 13, 5 squared plus 12 squared equals 13 squared, and so on. So we know a couple of these. And you might ask, what are the Pythagorean triples? Can we get all of them with some like algorithm that like generates a Pythagorean triple? And people have been looking into this for a long time. They apparently knew about how to do this back then. And Fermat also looked into ways of generating these Pythagorean triples. And he challenged another mathematician, I forget who it was, in seeing who could come up with kind of the biggest integers satisfying Pythagorean's equation. So, but how was he able to get
I don't
those?
think he, I mean, because I think that Euclid probably wrote up a number theoretical answer to that, right? Or am I
I'm
wrong
not
here?
sure.
I mean, I like Diophantus's method, which I'm sure is Fermat's method, which is you know, drawing this line with rational slope through a point you already have, and then the other point has to be rational. And this,
yeah. So there are some observations you make for this equation that if you say, let's relax this assumption about these numbers being integers, let's say they're rational numbers. Then if you have two rational numbers, if you add them together, you get another rational number, right? You find a common denominator and do all that business. And the third will be a rational number. If you square a rational number, you'll get a rational number. So if you know that x and y are rational numbers, you know that z is going to be a rational number. So you know some of these things. And from this equation, x squared plus y squared is equal to z squared, there's some kind of arithmetic you do, some transformations that can make it look like one of these things called elliptic curves. So you do some substitutions and create kind of these dummy variables to make this, but you generate this
where's the elliptic?
Curve.
Sorry, not in the x squared plus y squared equals z squared. If you're just looking for triples, there's no elliptic curve, right? You just, I mean, you just divide by z squared. It's x squared plus y squared equals 1.
Sure, that's one of the steps that you take in transforming this equation to a problem finding rational solutions to or rational points rather on an elliptic curve. So there's a series of steps. It's not all that complicated that you go through in transforming the equation to the equation of elliptic curve. And once you have an elliptic curve,
you must be asking a different question, right? About congruent numbers or something.
So elliptic curves can be used to solve what's called the congruent number problem. This is where you're looking for the integers n that are areas of triangles with integer sides. So the area of a triangle, 1/2 base times the height. Then you can attach an elliptic curve to that and try to find out if you have a rational solution and show that your number n is, if that's the area, that is a congruent number. So that's
right,
another problem elliptic curves solve.
We've kind of gotten just a little bit. I mean, there's this, I think some people must know this story that there was this Fermat wrote down that he could prove that there are no integer solutions to a to the n plus b to the n equals c to the n, where n is greater than 2. And highly doubtful whether he had a real proof of that. I think he had a proof when n equals 4, using this method of infinite descent. And people for a long time tried to prove it. And in the 19th century, they got pretty far with this method of factorization in cyclotomic number rings. But that method ultimately failed because you don't have unique prime factorization in all those rings. And ultimately, there's this story about how it was connected to this idea you could use this idea about the modularity of elliptic curves to end up proving Fermat's last theorem, which of course I have to say I don't care anymore about Fermat's last theorem at this point. I'm still confused. Like I've heard about this law. I've heard about this when I was 16. Okay, and I'm still confused about how this was actually done. So the thing I really now okay, I think we've left the lay people behind. I want to know about the proof of the modularity of elliptic curves, okay? I want to know what goes into it now. Now here's the thing, okay? I've heard the story many times, okay? Because I've asked people about this. I've tried to learn it. You know, I got this book here, and some others besides, okay? So I know some kind of story about how you know, you need to something about the Langlands tunnel and the theory of Galois representations, and how that's attached to a modular form. And then, but what you need, and what Wiles had to do was prove something called this modularity lifting theorem.
Mhm.
And I heard some talks. I mean, I tried to prepare a little bit, even though I don't know too much about any of this. And I know that today, maybe you actually don't need to go through those steps in quite the same way, because people have proved a lot more of these kinds of theorems, and the field has advanced. But I'd love for you to, what I want to know, okay, it's my theory as a mathematician. I want to know where's the work. Very hard for me to read number theory today, because number theory is very algebraic, lots of structures, lots of words and symbols that I have no clue what they are. You understand?
Mhm.
I don't like all that structure and formalism. To me, it's very concrete. I like to know, how many solutions can you measure, how many, etc. So I mean, I can believe, of course, you're going to use symmetry and use what structure you have, but my thinking is every time there's a new hard thing to prove, there's got to be some analysis. There's a key step. There's got to be something that you have to measure, something that you have to control. Where's the step? That's my challenge, and possibly I'm asking a challenge that I'm totally off in thinking that there's an answer here. But can someone explain to me where's the work? And I don't care about any of the rest of the story, but where I want to, I've isolated two key components here. That how do you prove that something is modular?
Mhm.
Period. And where does the work go? Does that question make sense?
Where is the work? I mean, it's quite a long proof that relies on some very deep insights by many people. So that book you have
Okay.
has a lot of details for those things.
Okay.
Um,
Okay. How about,
So I
let me
guess-
back up. Let me back up just one second then. Can you tell me, if you have all these deep bits that you want to know why and all this stuff, why is it so important? What is the point about this curves being modular? What's the point? What does it do for you?
So that if you know that this curve is modular, then that proves some results for you for the L functions of these curves, that they have analytic continuation, for example. You can't prove that based off of how they're defined. But if you know that they're modular, then it's almost trivial that you have those results. Those just kind of follow by those are very basic results for these representations attached to modular forms. So you get those two results for free once you show that a curve is modular.
I see. So in the case of like simple things like zeta functions or Dirichlet
Yeah.
L functions,
You get analytic continuation.
you get that immediately before you can prove that anything is modular.
After you show that your curve is modular, then you know that that means their L functions are the same. And you know the L function coming from the modular form has a functional equation and it has analytic continuation. You don't know that's true in the case for the elliptic curve or whatever abelian variety you're looking at, because those are defined with these local components, which involve counting points.
Right.
And it's hard to say if that is going to be, if there is a functional equation or that it does have analytic continuation. It's very hard to prove in that setting.
I see. What I was asking, I guess, for some of these simpler generating functions from number theoretical data, people are able to get, they form this, generating function, something called the zeta function or an L function, and using theta functions and Poisson summation, you already have a ready-made object that gives you this so-called functional equation to get the analytic continuation, right?
Right.
You have that thing, but you don't have it when you're talking about, these cubic curves and you're just stringing up, numbers of solutions.
Yeah.
That mod P, that you have no idea about. There is no object already there to get that. You need to prove the modularity from the start with nothing else. Although my favorite, going through Knapp's book, so much algebra. Finally, there's a real theorem, this Hasse-Weil theorem on the number, counting the number of points, an estimate, right? The defect from p+1 of the number of points on the curve has to be less than 2 square root of p. There's analysis. There's your hard step right there. I can point to it, and I know that's what gives you the convergence in a right half plane, right? Otherwise, you wouldn't know that. Is that right?
Right.
Okay. So here's what I'm asking is, where's that step in this proof of
Where's the
modularity?
analysis? So for the proof of Fermat's last theorem, which I don't know if we should say, you said some of the story already. That
you can probably say it better than me. I don't.
Okay.
I mean, look, I don't know what the hell I'm talking
So
about.
if you look at the equation x to the n plus y to the n is equal to z to the n, Fermat's last theorem.
Oh, but I don't want to. I sure people this about the Fry curve and the what this that part of the story I don't care about anymore. I've heard that story so many times.
Okay.
Let's just assume I don't care about Fermat's last theorem anymore. I care about this theorem about elliptic curves being modular. I want to know how, and screw Fermat's last, and we'll just assume, if you know that Fermat's last theorem will follow, and 150-year thing, whatever. I want to know about modularity.
So the proof of Fermat's last theorem involves analyzing these Galois representations that are attached to elliptic curves and modular forms. And actually reading through, once you understand the Galois representations of the elliptic curves and modular forms, and use this Fry curve, which is a way to kind of pass between the two, and there's some other results as well, that you show that Fermat's last theorem is false. So it kind of somewhat quickly follows from these bigger results of the modularity theorem that Wiles and Taylor-Wiles proved, that showed that rational elliptic curves are modular. Actually, they showed that these subclass of elliptic curves called semi-stable elliptic curves are modular. But that's all you need in this case. So
right, I gather, and then the whole all elliptic curves are modular was proven a couple of years later by these 4 guys.
Yeah.
Roy, Conrad. Taylor,
Diamond. Yeah.
Okay, but yeah, I don't know anything about that. I just want to know. It's like, see my confusion. How do you take this generating function, construct of these numbers potentially, or use whatever structure of the elliptic curve you have? How do you know that you could construct, I guess, as many coefficients as you like? You know what the modular form should be, but is it modular? Or I don't know, maybe that's not the way to do it. So how do you do it?
It's really showing that these 2 Galois representations you construct from the elliptic curve and the modular form are the same.
Okay. I mean, I've heard that. I guess so. The point is, you have to use, you're using something about the group of these symmetries of Galois group on the torsion points of the elliptic curve, right? I mean, that's
right. So to start making the Galois representations, you look at the p torsion points, and the Galois group will act on the p torsion points. It also acts at the p power torsion points. So you do this for all the prime powers, and you take this thing called a projective limit, and that produces something called the Tate module. And the Galois group acts on the Tate module, and that's how you get a Galois representation. You kind of build these Galois representations out of these local components. So you build some p-adic Galois representations attached to your elliptic curve E for all these primes P. And there's some theorems that you have to prove about something with ramification, that this Galois representation attached to the elliptic curve E is unramified outside of this thing called the conductor, which in the case for semi-stable elliptic curves, this term, the conductor tells you what the bad primes are.
What does that mean, ramified or unramified?
So that has to do with kind of the structure of the Galois group. So if you look at, say, the Galois group Q bar over Q, that's the completion of the rational numbers over Q, then you look at some Galois representation, say 2-dimensional in this case. For other kind of modularity theorems, it'll be a different dimension. But in this case, it's a two-dimensional Galois representation, some continuous homomorphism to GL2 of some ring R. Then you study these localizations of the rational numbers. So you take Q bar, you can embed that in C, and you can also embed that in QL bar, where L is a prime. It's getting somewhat technical now. So, but if that's what you want.
Yeah, okay. I guess it is what I want, because or we're getting to what I want. Let's see if we can.
Yeah.
There.
It's interesting giving this sort of talk without like a whiteboard to write down things.
That's true. Yeah, maybe is it the right way of doing it? I don't know. We're going to proceed anyway.
All right. So, so you fix these embeddings, right, of Q bar into C and these QLs, QL bars where L runs over the primes. And you look at the Galois groups attached to those things. So you have this group called G infinity, which is the Galois group of the complex numbers over the real numbers. So that is generated by complex conjugation, two-element group, very simple.
That's simple.
And
but this object Q bar and the Galois group of Q bar over Q has to be this incredible, crazy object, right? You're talking about all the algebraic numbers.
Yeah, so these are all the endomorphisms of Q bar that fix Q. So how do you get a handle on something like that? How do you get a handle on groups in general? You can study on how they act on vector spaces, which is what representation theory is about. So that's a tool that we use to get something out of this. So I defined the G infinity, this localization of the Galois group. And we also look at these GLs. This is defined as the Galois group of QL bar over QL. So these are called the decomposition groups. And you have these exact sequences of, okay. We have to draw a diagram, but there are these special groups called inertia groups that sit inside these localizations. And then the GL maps surjectively onto the automorphisms of the finite field FL bar.
Okay, oh, no. I'm getting a little.
So we want to define unramified. So basically the Galois representation is unramified at L if the inertial group is in its kernel. So it's trivial on the inertial group.
So just above it, lying above it are all the things, they all move, but it's ramified if it all comes from one thing.
Yeah, so this inertial group, it can cause some issues, but essentially ensuring that we're unramified at L, that means that our Galois representation, when we restrict it to GL, and we look at what it does when restricted to this localization, then that's completely determined by its value on the Frobenius. So you kind of miss some of the noise with this assumption. So we're looking at Galois representations that are unramified, basically have this nice structure that don't add a bunch of noise into this thing.
Okay. Look, I'm perfectly prepared to believe and understand, right, that somehow the group of all endomorphisms of Q bar that fix Q will act on these algebraic points on the elliptic curve, even as you take more and more of them, how many need to divide. I know why it's two-dimensional, right? And I'm sure there are some restrictions, but I want to know, and then I guess I'm sure you can ask, I don't know, I guess you can look at each prime, each localization, but I want to know, where is this, how do you go from, there's a Galois representation to there's, where is that, how do you produce a modular object?
Right, so now we have to look at the modular form side. So we started with the elliptic curve side, built up this Galois representation that's attached. Now we're going to switch over and do kind of a similar construction for modular forms. We start with some modular form and we kind of construct a Galois representation. So modular forms. So for like a brief definition, these are some special number theoretic function. They're defined on the upper half plane of the complex numbers. So the imaginary part is bigger than 0. And they satisfy certain symmetry relations. And they have some nice properties in that they have some growth conditions where they're kind of bounded at the cusps. They vanish if you go to I infinity, and they if you look at cusp forms, they vanish at each of the rational numbers that appear on the real number line below as like the base for the upper half plane. And these symmetries that they satisfy, one in particular shows that it's invariant under translation by one. So it's periodic in some sense. So you can attach a Fourier series to it. And the Fourier series has a nice form. It's the sum, and if you're looking at a cusp form, it has no constant term in the Fourier series. So it's a sum n is 1 to infinity of an times q to the n, where q is e to the 2 pi I tau, where tau comes from the upper half plane. So these are modular forms. They're just
it has that,
some
but it
big
also
series.
but it also has some other, it's with respect to not just translation, but some other thing, so that it's it's properly a holomorphic form on these quotient spaces, which are Riemann surfaces.
Right.
Right. That's yes. I mean, but you can't just tell directly from the Fourier coefficients whether the thing is modular, can you?
If you just look at a Fourier series, can you tell if it's modular?
Yeah. It has
So
come from it, but I mean, if you look at finally, you don't know, you can't.
Yeah, if you look at finely many, they might satisfy the properties. You might need to know something about kind of formal Fourier expansions, and if they satisfy up to some bound properties that a modular form satisfies, then is it modular? I don't know. That's something that I'm currently thinking about for kind of the degree 2 case,
Oh, really?
which is still kind of tricky. It's much harder in the degree 2 case.
I can only imagine, because I don't know anything about that case. I'm still in this degree.
We'll still, let's say down here in degree 1. So so you have these modular forms. Why would you look at something like this? So these modular forms, their coefficients tell you something about number theory. And in understanding spaces of modular forms, you can essentially show infinitely many theorems in number theory at the same time by looking at relationships with these things. So if you look at these modular forms that have some common characteristics, that they have the same weight, there's something called a weight attached to a modular form, and the same level, there's a level for a modular form, then you look at the set of modular forms that have the same weight and level, that forms a vector space, right? And these coefficients can tell you things like how many ways to write 8 as the sum of 4 squares and things like that. So you get some nice theorems out of understanding these modular forms and constructing a basis that has a nice form. You can produce formulas for counting such things.
Who's the first? Were these first defined by Euler or Jacobi?
Jacobi. So Jacobi considered something called the theta function, which is a sum over all the integers of q to the n squared. So if you want to count the number of ways of writing a number as the sum of 4 squares, then you just take 4 of these Jacobi functions, multiply them together, and then collect like coefficients. And then you'll get, if you look at the coefficient, which is a Fourier coefficient, then you can get that number. So if you also show that it's modular by showing that it satisfies these transformation properties and converges in the right places, then it lives in the space of modular forms. And if you have a nice way of constructing a basis in that vector space, these are all finite dimensional spaces, then you can show that this is a linear combination of these basis elements. And from that, you can get formulas for those coefficients. So you don't have to compute the Fourier coefficient each time with some kind of integral in order to get that.
Mm-hmm. Yeah, I mean, I agree. I mean, these things, you could just think of them as being, living in these spaces of forms on Riemann surfaces, and of course, it's all topological. How many? What's the dimension of all those spaces?
Right.
Right. But somehow these are also number theoretic, which makes them even more constrained, and they tell you even more. And I never. I know what more. I mean, there's so many mysteries to me that I'm curious about. Why do the coefficients of this J function are the sum of a couple of dimensions of the representations of the monster group and whatever the
Right.
heck, you know,
Yeah.
that's a different story entirely. But
There's a lot of things like that. And a common thing people say about modular forms is that they satisfy so many symmetries that it's almost impossible that such things would exist. But they do, and we can build them. But it's kind of surprising all the symmetries that they have and what we can get out of modular forms.
did people think that this had to be true because that this modularity had to be true because they had to be a analytic continuation of the L series of an elliptic curve? I mean, when was the Birch-Swinnerton-Dyer conjecture? That depends on this thing existing in the first place. How did they even, I still don't quite know what it means that they generated numerical evidence for it. You know, it depends, well, whatever. These are all confusions of mine that I have never figured out. I don't know the story of number theory in the 20th century. But forget about all that. I still am confused. I know what a Galois representation is, or so I think. And I think I know what a modular form is. And how do you get between the two? I'm trying to isolate where this work is that I still don't know.
Right. So in these spaces of modular forms, you have these things called Hecke operators. It's really a family of linear operators on modular forms. And you can look at what are called Hecke eigenforms. So these are eigenforms for these Hecke operators. So if you act on one of these modular forms, you get some constant times that modular form, and that constant is the eigenvalue. So you want to restrict
these. Yeah, I'm aware of these Hecke operators. This now we're talking about a really either a number theoretical or a group. You're really using this quotient property of the way you constructed this thing, right? What are these operators?
So these operators, they somewhat mess up the coefficients in a certain like well-structured way, but they have some nice properties in that you can make a space. Your basis can be a space of these. You form a basis out of these Hecke eigenforms to basically describe your space. So you're really putting as much structure as you can around these things and try to understand things in terms of these Hecke eigenforms as kind of like the building block for other modular forms. And since these are Fourier series, you often look at a normalized Hecke eigenform where that first coefficient is 1, because you can have just a multiple of that be another eigenform. So you make your space out of that. And there's a theorem due to Eichler and Shimura that tells you how to attach a p-adic Galois representation to these eigenforms. I think in their theorem, they focused on weight 2, which is the important weight. In this case, it's also the important weight in some kind of higher versions of these kind of modularity conjectures. So they show that you can attach this p-adic Galois representation that has certain properties to a weight 2 level n cusp form. So
for each p.
Right. So you have that this Galois representation they attach, it's unramified outside of the factors of n, the level of the modular form, and p. Okay, so you know what it's unramified out of, and you also know that you also get a formula for the characteristic polynomial of the Frobenius for primes p that don't divide the level of the modular form or this prime p. And you also know that, and this is where you get this connection between elliptic curves and modular forms, is that if f has coefficients in z, integer coefficients, then there is an elliptic curve defined over q, so elliptic curve with rational coefficients, such that its Galois representation, p-adic Galois representation, is equivalent to the p-adic Galois representation of the modular form.
And does this come from constructing that curve, you know, by taking the modular form and integrating it and putting it in, and you know, abelian variety, and the elliptic curve is in there somewhere, or have you recreated it? What is that? process?
Yeah, that's a good question. Let's see. Yeah, I don't remember their process.
Okay, but I that is at least, I can sort of imagine, I think, how that story might go. You're starting with something which is modular, producing something attached to an elliptic curve. But the other way, I mean, I think in some that's somehow described in even in Knapp's book. But but the other way is what is so is vexing me here.
What do you mean other way?
Going from the Galois representation to an object which is modular.
Okay, going back the other way.
Yes.
Right. Yeah, I don't know about that way.
That's the, but because isn't that the way, this is the, this Langlands tunnel theorem, right? That's one part of this proof. There's the Langlands tunnel, and then there's, I believe, this Wiles, it's proved this modularity lifting, which is the other part of it that I guess you can't just look at one field. You have to, if it's modular for something, then it's modular for a different field, one that actually matters, and therefore the elliptic curve is modular. And I don't understand that part either. But you see my frustration. I can't isolate where the work went. I can't read the papers or the books because they're filled with language that I don't understand. And these people, I think, they follow a philosophy that doesn't emphasize the analysis, and that's what I know. That's what I can get a handle on. Do you see what I'm asking? How do they do it?
Yeah, I just have to read those papers.
It can't just be this is equal to this, and this comes from this, and there's there's a symmetry attached to this. Somewhere you need to measure something. Somewhere you got to use, there's something about what are you keeping track of? What property is it that are you exploiting, and how are you exploiting that? You see what I'm asking?
What property are you exploiting?
Yeah, why, how do you, look, I can understand it's, I don't know, it's trivial. Once you have this functional equation, why the thing is modular, because you can do this inverse Mellin transform or whatever the hell, and can see that the thing respects the other symmetry. But if you don't have that, where are you going from? What property is it? How about, okay, maybe what property is it of this Galois representation that will tell you that it is somehow attached to that? I don't know, this, what is this, what are the numbers? The numbers you attach to that Galois representation are these determinant of 1 minus the Frobenius or something, right? And what is there to tell you that there's another product expansion? What's there to tell you that thing satisfies some symmetries?
Yeah, I don't recall that part, unfortunately.
Well, don't worry, because you're not the first. You're not the first person I've asked about this who I really wanted to know something that it's very hard for me to get into, and I don't even know if I'm asking the right question exactly, but I clearly don't understand what's going on in this field. I mean, some people must know because they've made some progress. Do you know, what about, do you know what Wiles did? Is there a step in his proof where you can identify some kind of, analysis, what needed to be looked at or measured?
So in this proof, he proved a lot of stuff about structures of elliptic curves, converting problems for elliptic curves to problems about Galois representations. And with the goal of kind of going through the Galois representation to prove modularity, his contribution for that part was proving this modularity lifting theorem. And there might be some analysis that you might find nice. So he shows that a semi-stable elliptic curve has a Galois representation that's modular. And for this approach of going through the Galois representation, to show that the representation is modular, you only have to prove it for one prime p. So he did some kind of tricks in switching because sometimes one prime is better than the other. So he had to show that if the Galois representation for one prime p is modular, then so are all the other related Galois representations. And he showed this using some things called deformations. And I'm not so familiar with that. I'm not so familiar with like the deformation theory.
But don't you see, of course I'm not. And of course, there's no way you're going to get me to start to learning about commutative algebra or knowing what the hell is a Gorenstein ring or whatever the hell. There's no way I'm not going to learn what are these properties until I'm looking at a definite thing, and that property comes that distinguishes the thing that I'm able to talk about from the thing I'm not able to talk about. You understand? I mean, so I can see this story that he something about the ring of deformations of Galois representations. He had to prove an isomorphism to this something called this universal Hecke algebra or something. I don't know. I don't know how you prove something is equal. That's how he proves some kind of I don't know, some kind of inequality. Something has to live after all this jargon. I just want to peel away I don't care about the jargon. I don't care about this story. I want to know what was the work.
Yeah. You keep asking what the work is, and there's a combination of kind of understanding structures of these things and then getting to, I guess you think of the analysis as like the diamond that really made everything all come together.
This is my view of math, and it's a controversial view. Not everyone agrees with me, and maybe this has been one of the obstacles in trying to talk to some number theorists. But yes, I guess I like to split, proofs up into the, you have the structure, the setting of the model, all the definitions, all the definite, and what is the setup. And you get as much as you can from that. Certainly in the field in which I worked, whenever there was a symmetry, you have to deal with that in some way. You mod out by that or what have you. And at the end of the day, you're left with, okay, now there's no more symmetries to take care of. You're just in the situation, and you just need to tell me something about, if the function solved the equation, is it this big or is it that big? Can I bound it? Can I say something about the number of these solutions? Can I that's why I feel there should always be, you're proving something new. It can never come from just an endless correspondences that just came directly from the definition. You had to get something that you didn't know. And there's got to be, I also happen to think there should always be an inequality there. Something is not equal to something else. Something is bounded by something, or it's contained in something you didn't appreciate before. And that's the part of it I'd like to see if that story links up with this, because it clearly they established some big thing, but I don't know how they did it. It couldn't just be philosophy. Yeah. It couldn't just be the definitions gave it to you.
It's a fair question. These are some deep results. So it's something I'll look into more in finding where there was this inequality that led to the proof. It
Well,
seems to be somewhere in these deformations.
or maybe the, okay,
If it's
so
there.
I don't know. And I mean, look, I think Glenn Stevens and his look, he outlined, he goes an overview of the proof, and there's all this jargon, and here's this Wiles numerical criterion,
Yeah.
and
And
here's an
there's
an inequality.
some properties that you have these Galois representations, the mod p Galois representations unramified outside, I think p and 2p, and then it has this technical condition that it's flat at p, and those kind of structural things were needed to apply some things like Ribot's theorem to basically remove all the primes except 2, so that you get that there is attached this eigenform to this elliptic curve that's attached to the Frey curve. Well, it is the Frey curve. You find this Galois representation attached to the Frey curve, and then you use these deep results by Wiles and Taylor-Wiles. And then Ribot's theorem basically says that you can remove all the primes because it's unramified outside of 2 and p, and it's flat at p, so you can take p out as well. And these theorems show that you have attached to the Frey curve, there is an eigenform G that is of level 2 that has the same Galois representation as the elliptic curve. But then you go back to the modular form side and say, so what is this G that would be attached? And you see that for weight 2, level 2, that space is 0. There's no such non-zero G.
Yes, I guess I heard.
So there's a lot of like these structural things involved that I guess I see more as like the main ingredients in these insights and showing structures about the Galois representations. But you are looking for
I'm looking for more information. It can't just come from the definition of a Galois representation.
No.
All kinds of Galois representations. Somewhere you're going to have to use something about solutions to elliptic curves, right? Somewhere you're going to have to use the specific structure. This is my another part of my philosophy of math. I hate too much generalization. To me, people in the Langlands, they love generalization. I think, the more general it is, the more trivial it is, because, I want to know what works at a specific case. Where are you using to the fullest the specific structure? Anyway, I was just going to point out that right here in this proof of something called Wiles numerical criterion, which I have no idea what the hell this means. Here's an inequality. This let this be the kernel IR mod R IR squared is finite, and this number is less than this number. Someone had to, that must be a non-trivial thing to prove right there. And I don't know what that means. I don't know what he had to use. And I mean, I think buried in all this jargon about Selmer groups and group cohomology, somewhere is like, oh, you need to show that the coefficients are congruent to this or something. I don't know what I'm talking about. But I can't even get into those chapters of that book full of language. But you see what I mean about, I don't know, I think anything you can know, you have to know it concretely. Like I know this concrete proof. I love this Stepanov's proof of the Hasse-Weil theorem. Do you know this at all? This polynomial method.
No,
I guess it became a big thing. You construct some polynomial that has zeros at all the places where this thing is 0, and deriving some contradiction. It's only so high a degree, and where these zeros can be. They use the same thing in this wonderful like cap set conjecture recently. Anyway, it's in. See, here's a book I like. It's got analysis.
Analytic number theory. Yeah. What do you like about that book?
Because there are techniques that I can understand. It's concrete. There's a clear problem. It's like, how large is this sum? Because the sum is exponential sum is encoding where the solutions are or something, and you have to find an inequality. You have to use the structure, but in the end, it's a result that's something fundamentally new. It's not look, I guess I have this whole theory of, if you prove all these things, that this is equal to this, or this is equal to that, you're really all you're talking about the same object. It's all coming from, it's just looking at the same thing in a different way. But when you really have something that is very unknown, is very, it's only known to you in a nebulous way, and you need to get some better handle on it. If you can prove, I can compare it to this other thing that I know better, that's new information. That's the kind of math, that's actually new knowledge. That's the kind of math that I want to do. And I strongly suspect that every time that you get something really non-trivial, if it's not just a consequence of the definition, it's not all these homomorphism theorems of groups. I mean, you constructed the definition so it would pop right out. But you want to tell me which ones are or how many finite simple groups are there, or which ones are they? You're going to have to say something about those particular groups. You're going to have to control them somehow. You're going to use something. So that's my theory here, and still don't know, but
right. So you also took an algebraic number theory class, right?
Yeah.
So was that not satisfying to you, kind of studying these ideals and looking at fraction fields or whatever?
Oh, you have to do that. Okay, I thought about this because, yeah, I must have. What did I learn? I know that I made a presentation in that course about Dirichlet's unit theorem, right? How many units, or was the dimension units? That makes sense to me, right? That's a question that makes sense to ask. It makes sense to ask. I don't know how far. God, I know we used the Lang's algebraic number theory text, which is probably not one that I like today. Actually, are you familiar at all with this guy H.M. Edwards?
I don't think I have any of his books, but
you've seen that name. This mathematician Harold M. Edwards. I think this guy, I only came across it relatively recently, after I had formed all my own ideas about algebra and analysis. This guy seems to have been someone, I think somewhat like me, who started out in analysis and then thought a lot about, must have been interested in algebra and number theory as well. And tried, I'm making up his story. I'd love to have him on my show, by the way. Must have thought there's something wrong with this whole world of the people doing this number theory and the way this modern way with all this formalism and the way they're thinking about things. I don't understand any of this. He looked at how it was actually done in the 19th century. And so his books, he's written several books that really go through, that help you to understand, here's the problem as it appeared to people back then, and here's what they did in order to figure it out. So he has this book, Fermat's Last Theorem, a genetic approach to algebraic number theory. Genetic in the sense of genesis, I guess, what was its development. And it's a totally different book from, I wish I'd learned from that book. Because here he's saying, like, here's, Lemay thought that he could solve for, of course, this book doesn't prove Fermat's Last Theorem, and it was written in 77, so it was before modularity was understood to have any bearing on this question. And he was talking about the approaches people took in the 19th century. And he shows you exactly how this guy, Kummer, figured out that you don't have the analog of the prime factorization that we know and love in the integers does not exist in every cyclotomic field. And how he figured that out. And it's great. This is step by step. I could see the problem, and even in this very algebraic context, Edwards says, here's the part of the proof that will involve analysis, and here's the part that will involve what he calls synthesis, algebra. That's a guide. This is the way I think about math, and I hope, I want to know concretely what people are doing, because I cannot understand anymore the Grothendieck, Hartshorne, you know, this whole way of looking at it with all this, to me, it's a lot of philosophy. It's a lot of language.
Mm-hmm.
And I want results. I want to understand things concretely. That's my goal.
So you're not satisfied with this going to Galois representations unless there's some, I guess,
of course I can. No, look, you got to use. I know that there's a symmetry group out there, and it will. And you have algebraic numbers with even more structure, because on the elliptic curve, these torsion points, you can use this to get this two-dimensional vector space. So you know that the group, when it acts on this thing, and it's forced to be in GL2 of FP or whatever, right?
Mm-hmm.
Of course you have to exploit that, of course, right? But it's not enough. That's not enough. That definition is not enough. Further, you got to use more than that. It's not just that it is this abstract thing not connected to an elliptic curve. It comes from an elliptic curve, which has additional structure.
Right. So maybe you'll find this a bit more satisfying. So modularity in like the 21st century. So I'm basically looking at a degree 2 version of the Taniyama-Shimura conjecture of basically showing that elliptic curves are modular. So for my case, I'm looking at these things called paramodular forms. These are Siegel modular forms of degree 2 with respect to this group called the paramodular group.
When you say degree, I mean, do you mean, are you talking about dimension? Like the dimension of the algebraic variety is higher, or what does degree mean here?
So you're looking at the Siegel upper half space of degree 2. So the normal case for the upper half plane, that's the upper half plane of degree 1. So in the degree 2 case, you're not looking at complex numbers, you're looking at matrices with complex entries that satisfy certain conditions. You want them to be symmetric, and you want the imaginary part to be positive definite.
Right,
So
but isn't this complex dimension 2?
This has dimension 3, actually. So I wouldn't use the dimension here for this space. Because it's symmetric, right?
No, but it's in, okay, what am I saying? You're taking, I know this construction, you're taking the, like, a torus in C2, right? And the, all these varieties are coming from.
Yeah, so I would say degree or genus too.
Right, and the genus is because they map the Jacobian of a genus 2 curve will map to one of these things. Mm-hmm. Is that right?
Yeah, I
the Jacobian map, or Hubble map. Yeah. I don't whatever this map is. You map a genus 2 curve to a dimension 2 abelian variety. Is that what we're talking about here? And it's what do you call it? The Riemann form, or that thing will have to lie in that Siegel upper half space that you were talking about, right?
Right. Okay, I lost it for a little bit, but okay. So you have the Siegel upper half plane of degree 2, and you're still constructing modular forms for this thing. And this will be similar to the last case where we develop a theory for the algebraic geometry side, elliptic curves in the degree 1 case, and the modular form side, where you have what are called classical modular forms. In our case, we're looking at paramodular forms as for the modular form side. And they are these functions that satisfy a bunch of symmetry conditions, and they're bounded at the cusps, which in the case for degree 2 and higher, for Siegel modular forms, you don't need to include this boundedness condition because the symmetries turn out to basically satisfy the condition by themselves. You don't also need to put some convergence condition in. So you look at these forms, and attached to these things are automorphic representations and Galois representations and so on. And you want to relate those to, on the algebraic geometry side, these special abelian surfaces. And you have to really pick out the kinds of abelian varieties that you want from the algebraic geometry side, because it's much more complicated there compared to the degree 1 case. So in the degree 1 case, you look at these abelian varieties of degree 1 that have a trivial endomorphism ring, which gives you elliptic curves, but you get many more options in the case, well, not that many more, but you get more options in the case for degree 2 when you look at the endomorphism ring of abelian surfaces with rational coefficients. Like you could have them be the integers, as like, that's kind of the most stable case, and that's really the one we'll be interested in. The other cases are that you get that the endomorphism ring tensor Q is a real quadratic extension of Q, or you get some kind of CM field of degree 4 over Q, or some indefinite quaternion algebra. So you get a lot of things from algebraic geometry. So it's hard to kind of pinpoint exactly what you need there. And people have been working on this kinds of question for a long time, and trying to find what are the right things to select from algebraic geometry, what are the right things to select from the modular form side. And it was only somewhat recently, I guess not that recent because it's been a certain number of years, but it feels recent to me. Brummer from Fordham and Kramer from Queens College, they came up with this paramodular conjecture that said that paramodular forms of a certain kind were attached to these abelian surfaces with a trivial endomorphism ring. And the trivial endomorphism ring was kind of critical here because they don't appear very often. They're kind of special in this case. The first one doesn't appear until conductor 249, and then you get kind of sporadic ones going up from there. And in this case, in showing modularity, we don't have like these big theorems from Wiles, Taylor-Wiles, and a bunch of other people to kind of show this in a more abstract level at the way that you probably wouldn't prefer. But we try to show some of these things computationally at least, and show that enough of these things hold, and then prove some kind of bound that we've shown that this is true up to the bound, and basically we've proven the dimension of the space and so on. So I've been working on constructing these paramodular forms, and we're trying to construct these spaces. We don't know the dimension of these spaces. So showing this kind of modularity kind of result would give us a dimension formula for these spaces, which we won't have in some cases. Some people have used these things called trace formulas to prove dimensions for some spaces, but they don't apply in this special case that we're looking at where the weight is 2, where these methods using cohomology won't work. They fail at exactly this level. And this is why this weight is an interesting case, not just for modularity, but because our dimensions kind of break down at this point.
Yikes. Okay, so you took away, some tools that I'm aware. I'm not sure I totally understand the setting because, look, I guess I know this. First of all, I'm thinking you're talking about something, a dimension 2, and I still don't know about the degree. It seems to me that, these abelian, higher dimensional abelian varieties, you could think of it as just higher dimensional complex tori. Is that right? But this SL2Z, which played a role in the complex tori in one dimension, that
Right.
was the operators that will preserve the same lattice, and so that's why.
Right. So those are the operators that preserve this Poincare metric on the upper half space.
Why are you bringing in the Poincare metric? That's
This hyperbolic metric there. So that's why this group kind of pops up, and the action, this action of linear fractional transformations. Why that is as it is, it's to kind of preserve this metric. So in the next case, you look at not SL2 or SL3 or SL4 or one of those, you look at the symplectic group, and that's going to act on these matrices. And this is some sense the way to go in the next
Because
step.
those preserve the you know, the form of whatever.
Okay.
But you're still looking at some kind of quotient space,
Yeah.
right? And you want forms on that space of, you're saying
Right.
the quotient
You
space.
still have some kind of like Riemann manifold, and you want to preserve something on it with the group action. And this is what you look at in this case as well.
And there you will have, presumably, you have not just one forms, but two forms as well, right?
Mm-hmm. Yeah, so you get these higher degree forms. So, right, so you look at, you have a question?
I'm wondering, does this tell you, I'm wondering if the object is to study the abelian varieties themselves, or say genus 2 curves of dimension 1, because those things map into those dimension 2 abelian varieties.
Yeah, I'm not quite sure what you're asking.
Also, by the way, also another confusion, something is confusion of mine that we didn't really talk at all about is how these quotient spaces parameterize or are moduli spaces for these objects in the first place, and what role that plays at all in this theory. Still a mystery.
Yeah. So yeah, there's a part of it. There are lots of things going on.
But
let me bring back to kind of like the analysis point in showing these things. So we have, so Brummer and Kramer, they come up with a list of these abelian surfaces. How do they get them? Ad hoc methods, basically, is the best way. So there's not a clear way to like generate these things, but those are not attached to these kind of classical modular forms. And we want to show that they're attached to these special paramodular forms. So paramodular forms is really hard to talk like this without like a whiteboard, be able to write things down. But so there are some ways of constructing paramodular forms from like the classical case. So degree 1, you take some kind of modular form, it has to satisfy certain properties, but basically you can lift it to become a paramodular form. And making some assumptions, you can control the weight and the level. So we're lifting to say the weight 2 form, and we want say a level n degree 2 form there. So with these things that are coming from lifts, it turns out that if you look at the automorphic representation attached to those and their L functions, it looks just like the L function for how it was in the degree 1 case times some like zeta and gamma factors out to the side. So it's really attached to an elliptic curve still. So we're not interested in those. We want to find new things. So these are the ones that aren't attainable by doing these lifts from classical modular forms. And those should be the ones that are attached to these like new abelian varieties, in this case, abelian surfaces, degree 2 abelian varieties. The other ones are attached to the elliptic curves that are down below. We have some kind of fudge factors outside, but we don't care about that. The main structure is the L function. So
I can certainly see how that representation theory is going to be more difficult if you want to say, these hard to representation in higher
studying the representations for automorphic representations for a GL2. All of those are what are called generic representations, meaning that they have these things called Whittaker models. These are useful in physics in some sense, but basically they have like an easily computable local components for those things. In the next case in degree 2, they're not all generic. Some of them are generic. You get into some mess of studying basically the L packets. So the representations that have the same L factors, but themselves are different. And in each of these L packets, you have like one is generic, but the others are non-generic. And the non-generic ones are trickier to deal with because they don't have, their structure just not as nice as the generic ones. The generic ones, you can define some like zeta integrals to actually compute the L factors. but it's hard to say what that is for the non-generic ones.
Okay, I can imagine. I'm a little bit lost. I don't know what an L packet is. I've heard that term before, but I can just imagine that it sounds like there's a lot of interesting stuff going on there. I was curious. Does it answer? Would modularity here? Is there an arithmetic question that would be answered by this theory?
So the degree 1 case, the arithmetic and not so much modularity, but what modular forms answer themselves without looking at what additional things you learn from elliptic curves that are attached to these modular forms. So these things, these counting problems, numbers of ways of writing integers as the sum of n squares, for example, that's there. And in a sense, I think that is still being there in the case for degree 2. They're just kind of more, they're further down, because in this case, you have that the coefficients are infinite series themselves. So you get tons and tons of these things. For paramodular forms, you can write them as some kind of Fourier expansion, but you don't really have Fourier coefficients. You have what are called Fourier Jacobi coefficients, where the coefficients are Jacobi forms. And Jacobi forms are some kind of, it's basically like a twisted kind of classical modular form, twisted by the action of some Heisenberg group. So you have kind of modular forms where it's q raised to some power times another, like a classical modular form, and then the sum of all those. So it's much more complicated, where you don't just have like a single number as the coefficient.
Yikes.
So,
my
so let's analyze these things. Let's dive deep into the analysis. Jacobi forms we understand very well. We know the dimensions of those spaces. And from the structure of these spaces of paramodular forms, we know the structure of their Fourier Jacobi coefficients. So if you have a paramodular form of weight k and level n, then the first Fourier Jacobi coefficient, all of them, by the way, will have the same weight. So you know that at least. And the first Fourier Jacobi coefficient, the 1 times q to the n, that first Fourier Jacobi coefficient will have index, they call it index instead of level. It has index n. The next one, that's the coefficient for q squared, is going to have index 2n. And then the next one is 3n, 4n, 5n, and so on. So it has this very kind of nice structure to those things. And that is, I think, a better way of looking at those than just as their Fourier expansion. Because the Fourier expansion, there's not a clear way to like order things. And you look at these, they're ordered in some sense by matrices, where their entries satisfy some particular equation. So it's a big mess here. So
Okay,
how do we understand those? We can try to construct those series by understanding what Jacobi forms can we place at each of these coefficients, and understanding all the symmetries that these have to satisfy because of these kind of factors of automorphy that come out. Like you have in the classical case, the c tau plus d to the k as a factor that comes out. You have a similar kind of thing here. You're dealing with matrices, so you're actually determinant of some matrix to the kth power.
Right.
And you look at all these symmetries and how they affect the coefficients, and you say, how many of these Fourier Jacobi coefficients do I need to know before I know all the form? Because the symmetry should cover a lot of things further on down the road. And there's some loose bounds for that you have to know the weight up to the weight k over 4, I think, is a bound, but that's many if the weight's, sorry, that's the wrong one. So there's some formula, I forget exactly what it is, as like a loose bound where you have to go way out there to find all these coefficients. But you can start kind of one by one.
Sorry, I'm lost. I don't know any more about these paramodular forms. I only know by analogy to the lower dimensional case. And I mean, it sounds like people have studied this and that there's a lot of intricacy here. I just...
So I guess let me leave you with like the main point. So from the symmetries, you get lots of equations involving the coefficients that they have to satisfy. And then using that, you can say that if I know the Fourier Jacobi coefficients up to the, say, mth one, then I know all of them because the symmetry relations tell me all the other coefficients. So then you try to construct these things. So that there's your inequality that gives you a bound that we use that involves like counting things and what happens at the cusps and so on. But whatever, we get this bound that once we know that, then we just need to compute these coefficients. But these Jacobi series, those are infinite series in themselves. So we need to also determine how many of those coefficients we need to know to determine the Jacobi form. And we need some way of constructing each of these Jacobi forms. And then once we have that, we can write some algorithm to compute a basis for those spaces and then try to fit them in, these kind of pieces to this puzzle building in paramodular form.
You know, to me, I feel like if there's still interesting and hard questions in the supposedly simpler case, I'm gonna stay there almost probably my whole life and never look at the the next thing, because I already want I want to know elliptic curves over Q. There's still unsolved problems here.
Right.
But I guess some people are going further.
Yes. So what I like about this is that in studying these kinds of questions, you can really study this from lots of different perspectives. I approach it more, I guess, from like the algebraic side, but doing some kind of analysis myself and actually looking at these coefficients and how many I need to know to determine what that is, have some kind of bound, and actually use that to solve these dimension problems. So that's one thing you can do. And also there's a lot of symmetries here. So you find all sorts of interesting things looking at kind of the low level of things, but also kind of expanding up to look at the relationship between these kinds of modular forms with algebraic geometry and automorphic representations, and what you can get out of understanding the structures of all three.
I hope you get something. Okay, because I don't know anymore. You've exhausted my ability to know what you're talking about. I want to switch gears a little bit. I mean, you must like this subject a lot because you are doing it on your own and you're not in academia anymore, which is the situation I'm in myself. And I want to know about that. How does it come that you get your money from working in data science, right?
Right.
How did that happen? If you're willing to talk about that.
So in investigating these questions on modularity for the degree 2 case, it involves lots of computations that I did with Python and Sage and things like that, and was reading about how to manage large data sets, because I'd have these huge matrices filled with coefficients of all these Jacobi forms and trying to compute co-ranks and things like that and show when they go to 0. And I started reading about the stuff that Google was doing in machine learning and image classification with all of the great stuff there. And it seemed like that would be a better position for me, and kind of going outside of academia to get this data science position, where it was more kind of a research focused thing. I do miss teaching. I love doing the teaching aspect of that. But it seemed that you had kind of more control over where you were if you went into data science rather than stay in academia. Because academia, there is so few positions out there, and PhDs just keep going out. And you're lucky to get a position. I was fortunate to get the postdocs that I got. But then after that, it always seemed like each time I applied for jobs, it was kind of throwing the dart at the map. I happened to get my top choices in almost all cases. But then after spending some time as a postdoc in New York City, I decided this is the place for me. So how can I make sure that I get to live in New York City and enjoy being here doing math, which I can still go to seminars if I like. So that's basically through the best chance of success was going through industry. In academia, you could get a job at the many colleges around New York City. They also have adjuncts that are adjuncts for many colleges, and they spend their time kind of commuting around the city.
You don't want to be one of those
guys. Not get benefits and things like that. It just seemed like a punishing lifestyle,
Yeah.
which being in New York City is already can be punishing enough. So I didn't want that to be like an added thing on top of it. So it seemed like this was a better route, a more sustainable route for me, so that I can also have time with family and choose where I get to live.
Well, so, but okay. So I guess what I'm interested, I didn't know that you already came around, in your own work, in your mathematical work, you were already doing the kind of work that somehow naturally led into some of these
Yeah.
issues in data science, which is not the case with my work. I'd never, I've practically done nothing on a computer. I guess I had to do a couple of computations in Mathematica or something.
Yeah. I've had a strange route, I guess. Going into school, I was interested always in computers. I thought about doing like computer science, and I actually was a computer science major. My first semester, I was interested in AI and all that. But after kind of the first semester, it became clear to me that I was more interested in the mathematics behind it. So then I jumped full on into that and just found, I know you hate this word that people use for mathematics, but I found the beauty of mathematics much more satisfying than the stuff I was doing in computer
I'm sure
science.
I'm sure if we parsed it, we could find something more specific, and it wouldn't just be beauty, a word that people bandy about like it's just an answer to anything. Why do you like math? And clearly there's some people who don't like it at all or don't know what it is, and you just say, well, no, but it's so beautiful. What the hell are you talking about? I could tell you what I like and what I don't. Well, whatever. No, of course I can see. I don't know. People could be drawn to math and not computer science, or I was somehow, I took math and physics, and I like the real world too. But somehow I felt myself drawn more to the way of thinking and kinds of concerns, the problems in mathematics.
So for me, it's been, I think I started more on like the analysis kind of camp in these things. I really enjoyed my real analysis classes as an undergraduate, and I thought that's what I would be going into because I liked just how precise the proofs were. I wasn't so satisfied with abstract algebra and like these cute little tricks in group theory where you learn this thing, and if you multiply it in this order and put it like this, then that's how you get the proof. I just found the proofs more satisfying in analysis. But then going through school and being exposed to more algebra, it's, I don't know, I just kept being more and more seduced by the algebra side of things to lead me away from analysis. But that was still a component, I guess, that I've
Very
been
hard to know.
interested in.
In general, as an undergraduate, anything about, you could take all the classes and it still just practically gets you to the year 1900, and you have no idea what it means to really work in math. Doesn't matter what subject you're learning, I think. But yeah, I mean, you're a real, look, I guess what I want to know, I mean, if you could make it work, you'd rather be a professional mathematician, right?
I don't know. I don't know. I enjoy that. I also enjoy data science a lot.
Okay. Because
like,
I know that I saw so many people. I saw all these lots of smart people in math along with me, and I know the ones who were in it, and I know a lot of people who left, and I know they finished their PhD. Most of them finished, but they sort of knew that math is not what they wanted to do, and they prepared themselves for a world a lot of them in the world of tech, some in consulting and finance.
Yeah. I did not do that. Like
no,
I was planning to stay in math. I didn't have a plan B. Like it was like this or break or whatever.
That's right.
So I was just fortunate in that the things that I was doing surprisingly led to things that I could apply to other problems than just number theory. I was fortunate in, so my thesis in my work in graduate school was more on the abstract side in understanding some representations and defining functors and doing stuff in category theory and stuff like that. And I became interested in this kind of paramodular conjecture and doing computations there. And I also, I had a mathematical license at grad school, And I knew that that's very expensive. I didn't know what school I ended up, if they would have the budget to cover that, or if I wanted that to be covered. So I thought I'll learn Python and use Sage. And that turned out to be a very fortunate thing to do because it became big years later in data science.
Yes.
So I did that, did lots of Python programming throughout kind of my postdocs and doing lots of stuff for research and also making these components for classes I was teaching. Really just kind of happened to gain the right skills to move into a career in data science through my work in academia. So I don't know, I just feel kind of lucky and happened to pick the right things, but there was no plan for that. And when it came towards the end, when I decided I'll finally move from academia to industry, then it was more, not so much that I was dissatisfied with academia. I just found that there's some things that are not so pleasant in academia, like the length of time it takes to get something published and going through that process and how much teaching you have to do. And you might not have enough time for research because of that. Whereas in data science, you're doing research most of the time and trying to understand something. In this case, problems aren't as structured as they are in algebra and number theory. But I do like spending time and just really like thinking through a problem, I guess, doing the analysis, as you would say.
Yeah, well, I guess I've tried, in my own journey, I guess I've had to learn. So everyone is studying this machine learning. So I took some online course to see what this is. I don't know, I guess I can get some of it. It's hitting me with a lot of stuff because there's statistics, which I never learned, and a lot of computer science, which I never learned. And there's a lot of, all kinds of things are going into it. And yet I can do the exercises that they tell me. I just don't know, how am I ever going, I don't have the technique, the same level of, I'm not an expert like I am in the math that I do. And not only that, it's also a field where the currency is not a theorem. It's, can you classify this thing a few percent better or whatever? And it's not clear, is it doing it better because I've solved something, or is this just someone's, what's really going on here?
Right.
And I think there's a lot of statistics and some other things in numerical methods that are not things that are so deep with me. It's not, hey, this is not what I trained to do. I trained to do a particular thing, why am I being forced to leave? I guess, do you know this guy, Peter Thiel?
Yeah.
I mean, he says, look, all these people are getting PhDs, but do you know in which disciplines? There's only 2 disciplines where, I forget what is his statistic, some substantial number of their graduates, proportion of their graduates, actually work in the field that they trained for, and that's computer science and petroleum engineering. Everyone else is screwed. There's not enough positions. We're learning, we train at math or physics. I think physics might even be worse. There's all kinds, they're all worse. And then there's, I thought I'd be a professional mathematician, like a professor. And now what? Now what do I do? That's not there. I mean, no one's paying me to solve these problems like I thought they would. You're able to keep up with it, which I'm very impressed by. I mean, the fact that you keep doing it even while you have this other thing. I mean, if you really love this, I don't know, if you love this data science, you'd be doing that in your spare time, maybe solving some problem about that, right?
Right. So I think a person can have more than just one interest, right?
Yeah, okay.
I mean, it's all like technical things. So in my spare time, like I do read about kind of machine learning stuff and data science and statistics, as well as math and other things as well, history, novels, and I'm always reading something. So
I see. Yeah.
I don't know. I never like, there's only one case where I made a decision, like picking like the best interest to make a commitment to, and that was going into school. I was deciding, should I study computer science or history? So I made a decision
undergrad, not
undergrad. And I decided that computer science, I could do something with history if I became a teacher. That seemed, even to me at the time, like a very competitive kind of thing. And I don't know, I think I would get more enjoyment anyway out of doing math and understanding kind of technical things. But I still kept that interest, even though in grad school I didn't have that much time to read history. I am finding that now I can diversify my interest, at least the time I spend on the interest, more in data science than I could in academia, which I appreciate, and not reading papers directly in my kind of subject area so that I can work on kind of the next paper to get out. You can really get sucked into a particular subject and spend all your time thinking about.
Yeah, I mean, I did have free time as a postdoc, but yeah, it's very hard to know. I mean, you're right that as much as a person loves history, unless you're going to be one of these celebrated historians, and it's not clear to me how one gets to be that person. What's the difference between that person and the person? It was a couple fewer publications, and they can't.
Right.
That guy, and it's similar thing in math. I guess now, do you think? Well, maybe you don't have as many grievances and sour grapes as maybe I have. I want to. It won't do me much good to air them. I just what should a person do learning math today, right? Because it's it's hard to say that there's going to be, there are lots of people who love math and would study it and almost certainly would contribute, I think, a great deal to the mathematical knowledge. And I'm wondering, do we even care? Is that even what we want? Because look, unless, they take so many grad students, but the professoriate is not growing at the same rate.
Right.
So what is it they think these people are going to do?
Yeah, they don't really prepare you for that in grad school, at least not any that I know. I mean, some are making some changes with data science and having that be part of the program, but you're not really trained in graduate school to go into industry. You're trained to be a professor.
Right.
You're directed in this way that there just aren't those positions for everyone. So you need to have some kind of backup plan, I think. And it doesn't have to really take up that much of your time. I think just learning some basic programming and linear algebra and probability and statistics can get you pretty far. And coming at it from kind of a mathematical mindset, you're able to understand those subjects at kind of a deeper level. At least that is my hope, that you can, that us going through whatever training in mathematics that we've had, we've learned how we can approach problems, what structures exist around problems, and how we can really use what's available to get to something a bit deeper than someone who has not had that training, but is still doing some like science work.
I mean, I can imagine that some of that is true. I mean, yeah, you've had mathematical training and now you could do this other task well, but there's so many things that bother me about this, what you just described. First of all, that there's the people who are totally, if you really want to go all the way to be a mathematician, it's almost like you really have to be all in. You have to be doing it in a way that shows a commitment that maybe you don't have, that you're not doing this other stuff. That was never on my radar, the doing something else. And of course, in that decision, there's the like sort of, who do you tell? You are on the track. You can do it. You're like the good, and then here's who's. Is it the people who are good versus who's bad, or won't?
I don't think it's that. I don't think it's good versus bad. I think there's a lot of luck to it, because there are a lot of good people who just don't get jobs in academia.
Yeah, but and then further than that, though, look, here's something that bothers me. There's the thing that I loved and lived in for so long. Could I learn this other thing and be I don't know, could I train to be a software engineer? Maybe, but I'll never be as good at that as I am at this. I'll never be the person. I'd be competing with people who, you know, there are people who love programming and love software, love computer science.
Mhm.
And they've been doing it now, you know, 10, 20 years, you know, when they're my age. And you know, I'm just starting. I could do it. I could be average at it, but I didn't sign up to be average at the thing that I did. I signed, my plan was to do the thing that I loved and was great at,
Mhm.
right? It isn't, what do you think about that?
I don't know. I
That
think you could
attitude?
get there if you put in the time to understand it.
Oh, to do that some other thing. I mean, sure. I mean, but I feel like I'm doing whatever I can in order to get back. In order to get back, when are they going to, you know, hey, they respect that other guy in math. I want them to respect me. How am I going to get back there? Is my only the
Okay,
question.
so to go into industry to do work and with the intention of going back into academia.
Well, the thing is, at this point, it makes no sense. On some level, look, at my thoughts are all jumbled here. So I'm just, if I say a bunch of contradictory things, that's. I mean, I came up in this world where who did I know? This is professors, and I thought I should be like. I saw the world of how the respect afforded to someone big who comes to give a talk.
Mm-hmm.
That's the world that I did. That's the world in which I thought that I thought mattered. Now I'm now seeing, you know, in some ways that's a very small world,
Mm-hmm.
and there's another world out there where they don't know any of those people. And guess what? It's important to have money, and there are other people who are able to do things. You know, I guess I never really thought too carefully about exactly what I was after, because as much as I wanted to be a professor, I also wanted to be someone, I don't know, like Elon Musk or Bill Gates, lots of power, and is that changing the world with at the front of a company, the captain of a ship, right? Not that I ever did not even one thing to emulate either of those people. I just always thought I'd somehow be that person anyway, which, you know, stupid thinking on my part. But you know, I want it all. Why can't I do the kind of work that I love and am good at, and, you know, get all the other things I want out of life and not be at the mercy of any of those other forces, and not have to you know, be under pressure to produce more than what little I did, because the tenure process would never have come through for me, even if I'd gotten a job. So I mean, I don't know. I don't know what to make of this, other than that I hold in my head these contradictory ideas that I think that I'm good, and yet they wouldn't give me a job. And I want to do one thing, but I have to do another thing. And I don't know what to do exactly. I thought the world would pay me to solve some hard math problems that the world needed solving. And I guess I thought, I wondered if that was the same way you thought.
So transitioning from academia to industry, I definitely felt that I was coming out of a bubble in some sense, that it was much more closed off, where there was like one defined career path. And just kind of being there opened my eyes a bit more, being there as in out of academia, after having had all this training with kind of this kind of one track mindset to like go to tenure track professor, and that's my destiny. I'll get that. And just, I don't know, coast the rest of your life and solve interesting problems. But in moving out of it, it's kind of made me see the world as a bigger place. And I don't think you're ever guaranteed that you can get everything that you want. No matter how much you like demand it, and I'm doing all the right things. This is what someone does to get there. And
I didn't do the right things, so.
Yeah, and you don't really learn some of these skill sets in grad school. At least I didn't in that you kind of need in having a business mindset. It seems that's kind of common for mathematicians who transition into industry or data science, that they don't really think in terms of a business mindset and like how, like, what would this mean if I solve this problem? It would mean that this company can make this product and it'll sell this many millions or whatever. I think
Never
we
been
become too
practical.
focused on actually solving like the mathematical problem. But when you get into some data science type roles, some of the work is just very trivial. You're not even doing linear algebra. You're just computing things, adding stuff together, multiplying, dividing, and basic stuff like that. But being able to take all the stuff that you're computing and try to think about what that would mean for a business is a different skill than what we're taught in grad school. And that's not something that you can't ever learn because you've gone through this training in mathematics. It's just something additional that you need to pick up.
Yeah, but every
And
time I talk to someone about this, it's almost like they need to strike me down. My attitude is always wrong. Of course, I learned how to judge the merits of taking a particular research direction. I learned how to judge whether a problem was good, and it had to be, you know, the merits of it had to be important to solve, and it had to be possible to solve, right? I knew how to sort of gauge that. And of course, it's a slightly different thing what you're talking about. And the whole world has told me every time I think, you know, I want to help the world. I want to do something that has value. I thought I can solve a math problem and then it will lead to a thing you can do in the real world. And I can understand even a lot of the history of math to be a lot of people doing those things. And yet everyone tells me that's not, that almost never happens. Almost always it's doing these trivial things. You can't wait. You can't just go, and no one's going to give you money to spend years trying to solve some other thing. You got to do something now, the kind of task that for the most part, I feel that I'm above, that there's some programmer who can do that, and that's not my skill. And that of course is the attitude that makes people say, we're not dealing with this guy at all. And then now what do I do? That's the okay. I just voiced my frustration. I guess I'm trying to be better than that attitude. But what you're saying though is like, keep math the same way, but tell grad students that they need to prepare for an exit, which could be the same in a lot of the scientific disciplines. It makes no sense to me. These people are learning science. Why? One, maybe this country should pay, invest in science. I don't know if that's the right thing to do. Get more science, or maybe these disciplines need to change. I mean, they need to change their emphasis and decide to be of actually producing value, so that they can grow. And math, there would be emphasis on totally different topics and different skills. I still think it can be good math and something people can do. I don't know exactly that would look like.
So I'm generally against designing education programs to be around some practical result that you can get out of it. But I think that should be available to people, and that should be brought up. Like this is the thing. Give graduate students like a clear outlook of the situation that they're getting into. They're going to dedicate themselves for studying 4, 5, 6, 7, 8, 9 years in this program, and these are the subjects that this math department excels at, and they'll probably go into one of these things. Let's say you go into number theory, very abstract, but you also have these other parts of the graduate program that could be redesigned so that if you wanted to have the option of getting yourself kind of a plan B and taking probability and statistics or kind of a data science type program. So at least you have at least some training in those areas. You can decide, of course, not to take those and just like bet it all on number theory or perfectoid spaces or whatever.
To be honest, that's probably what I would have done even if I had been made aware of that stuff at an earlier stage. But
I think so too. I think even coming in, you're aware like you can make more money doing computer science. And still I made the choice to just go into mathematics and number theory.
But I'm actually now thinking that good math is the valuable math. It's not this abstract, won't help anyone in any way. I believe in concrete problems, and I think you can there are concrete problems within number theory, and there are also concrete problems. I learned none of what is called applied math and how things are actually computed in the real world, or what people actually do. And now I'm thinking now that's actually, it's not like it's bad math. It's easier not for the elite mathematicians to do. That's actually good math. That's actually good stuff. That's hard. It involves lots of complication for whatever sociological reasons. It's just somehow not ended up in a math department. But these professors, I think, have the wrong incentives because the system worked for them. They don't need to think about, they don't think about their students, what will they do? But the program needs to be redesigned with different incentives, a different outcome, so that people will do it and know that they're going to come out and not be someone trained in a thing that no one is hiring for. Something is really
well, hopefully your advisor tells you about that. And often your advisor can help you find a position after school. But in choosing an advisor and deciding on kind of your research project for your thesis, that should at least address some of those things, right?
It should. I hope.
Yeah, but as far as like good math and deciding that you've solved this great problem, and because you've solved it, the world owes you this. I don't think you can ever like put that expectation on it, no matter how, even if like everyone agrees like it's a great problem, still.
Well, I feel like it used to be easier, but it wasn't quite so competitive, and now it's very unclear what people are going to be doing. I mean, let me put it to you this way. Would you even, I don't even know if I'd advise someone is bright and likes math, coming into school as an undergraduate. I don't even know what to tell them anymore. I know what math is. I know what to tell them if they want to learn math, but should they learn math is really the question here. I mean, I just, because if in the end, look, if in the end you're going to do data science, there are other things that you can learn that will make you better at that thing,
right,
than learning math.
Yeah. I think this is not a new question, right? I think Sarah said that whenever someone asks him about studying math, he always advises them not to do it. Just don't go into math.
Yeah.
And the ones who are really dedicated to math,
too many mathematicians, I think, is something he said. Yeah, I've always frustrated. I've come across a couple of people like that, and of course, they always frustrated me. I wanted them to know, hey, look, I'm good like you. You should treat me like
right,
one of the people not one of those people who won't make it, but one of the people who will. But I don't know. I don't know quite the institutional solution here. It's just clearly a serious problem. I know more and more mathematicians who, it's not like anyone gives you credit for doing something very hard and that you can move into something else. They're looking at candidates who actually do the thing that you're supposed to do in computer science or whatever, and they don't care that you solved a different problem in a different area of science. I don't know. So I'm glad that the transition worked for you. You can live in the city that you want to live. I want to live in New York City, maybe not, during coronavirus, but maybe when it recovers. Any big city, I suppose.
Yeah, well, I got some help too in doing one of these like data science boot camps to help me transition out of academia, because you go through academia and you don't really build business contacts for the most part. Maybe some people do internships over the summer, but mostly you're going into this brand new area where you know no one and don't really have exactly the right training to enter. So there are lots of challenges to be solved to kind of make that transition. And then to find success in your roles, you really have to kind of spend some time to learn how to think in a different way, I suppose.
I thought about that insight data science program that you did. I don't know. Do you even know that? My guess is that they're probably much more selective now than they once were. That you already.
They've had big changes. They've had to let a lot of people go, and they're charging now fees to the participants instead of just charging the companies that hire them. So they've had a lot of changes. Lots of places were impacted by all this stuff with the coronavirus. So I've just been profoundly lucky, because many places are laying off data scientists, whereas I've been pretty stable in this environment.
Also, by the way, it worries me that so many people are all doing the same thing.
Right.
To do
but the thing I think for mathematics and for mathematicians who would spend some more time in trying to really get into more of a business thought process, I think they can find a lot more success in these types of roles and more enjoyment in them. Because you can read a bunch of data science posts and machine learning posts on like Medium of people like just starting out in learning, and you read through their choices in the design of this project, and you see like, obviously there's a much better thing that you could have done in this step. So I think mathematicians are at an advantage because we can see more flaws in someone's work, and that can help us in coming up with a better process.
Maybe I'm trying to learn, okay, so I'm trying to learn some of these things myself. I'm even trying to have my own business that does some of this, the machine learning and this other homomorphic encryption technology. And so I guess I'm trying to understand what other people do. But you know what, it's like I bring what I have to it, but I really would prefer to be working with experts who can appreciate why this paper from Google or whatever it does better. Is that the right? I don't know. I mean, I can read it, I can judge, the results or something, but
yeah,
no.
I mean, it's good to talk to these people who are really into machine learning and understand things coming from more, I guess, computer science background that we just don't learn in mathematics. So math grad school doesn't teach you everything that you need to know.
Almost definitely not. And of course it teaches you even, I mean, you're in a track, you should learn your field very well.
Yes.
I know what it is to be a scientist. You're not supposed to know everything.
Yeah, you can understand something very deeply, and going through successfully for math grad school shows that you have that ability to get to that point where something that can be extremely abstract and maybe not useful to anyone, but you understand it very well, or something that could be more useful if you are going on like the applied mathematics kind of route. But you still you're developing that skill to dig deeper and deeper into something. And I think that's something that puts mathematicians more at an advantage in these positions.
But no one hires mathematicians.
But no one hires that. So I think I have the same flaw that you do, in that coming from mathematics is this special thing, that understanding mathematics and solving mathematical problems, those are like the bright stars in the sky, and everything else kind of pales in comparison to that.
Yeah, that's the view.
The world doesn't revolve around our vision of these stars.
Yeah, there's a harsh realization, I guess. And yet I'm happy to work on any kind of problem. I mean, I'm going to work on it as a mathematician. I just want to be a mathematician in some capacity. Do you consider, I mean, would you consider the work that you do, is it like mathematical work, or is it something else?
I think of it as something else. Yeah. When I think of like the mathematics of the work, it's more, I guess, the operations that I do, and I'm not sure how to put it, but yeah, I don't think of it as, I think of it as like data science, as something that is distinct from actually doing mathematics.
I've got to believe that somewhere out there, people actually need problems solve that use my skills, and I won't be just a programmer. Like, come on, I realize that a lot of it has to do with, oh, you gotta, format the databases correctly and whatever. And I view that as the trivial part. Like, let someone else do that. But
yeah, like the trivial parts in doing the computations, it's just arithmetic, which I don't really, it's part of mathematics, but it's not what I think of when I say the term mathematics.
Yeah.
Right.
I think about solving unsolved problems.
Solving unsolved problems. I think of it as understanding something at a deep level too. So that has a certain structure and understanding different components of it and how you can put the components together to make something. But for like the data science perspective, I don't really see it as the same as mathematics. You're still finding like insights for things, and in some sense you're solving a problem, but the problem is finding out certain facts and understanding how that could influence something about whatever business you're working for or people in some respect. But it's different from math.
Yeah, no, it's experimental. I mean, I can imagine, oh, you do some clever thing and it works better. Now, I guess as a mathematician, the idea would be like, you should prove, there should be a theorem there, right? There should be something you can show it, some measurable benefit.
Right.
And it's not, it's so that it's not a fluke. And probably if you used a big enough data set and you tried it a couple of times, you probably convince yourself it wasn't a fluke experimentally.
The stuff in wanting things to be so precise that they're exact, in mathematics being like the purest form that you can get of any certain statement. So mathematics is both like the theorem, like a clear fact about something, and all the work that goes into coming up with that fact. I think of that as doing mathematics. For data science, you're not really coming up with, you're kind of coming up with facts, but they're not at like the same kind of deep level that you have on the mathematics side, right? You might understand something about population, that for this group of people that buy this product, 30% are type A, 20% are type B, and they have kind of these sales patterns and so on. You're basically doing arithmetic to come up with those shares. And the insights in data science are really getting the so what out of that. Like, what's the use of this fact? So it's kind of thinking of these kind of more trivial facts than you would find in mathematics, but needing like this insight theme, like what do you do because of that?
Well, I guess I'm thinking, one, I definitely should have taken a course in statistics. I don't know why that's not part of math. And I'm also thinking a lot of these things you're saying, I don't know, if there's already some procedure figured out as to how to optimize this or that or whatever, and you can churn it through a machine, then I feel like there's no room for me. Now, if you have a problem, if you have, oh, we would do it this way, but these matrices are too big and we need to know how to approximate something, bingo. Okay, now you're talking about a problem I can attack or something. But until then, I just don't know, how do I do this, contribute any better to this than, I don't know, some other guy. I don't know. So that's why I'm trying to, I have to develop a new technology to solve a problem that there doesn't exist a market for yet. And that's the only way, because that's how I'm doing it. But you're okay, and you don't want back in. Why continue? You do math because you like it, but are you trying to get them to, I don't know, maybe you don't have my disease of wanting people to recognize you. They love this guy Peter Schulze. Where's my meta? Where's the theorem? Where's the Wiles proved this Fermat's last theorem? Where's my theorem? What am I gonna get?
Just pick one of the Clay Millennium Prize problems.
I like BSD. We'll get into it. If I could understand anything, I could understand Gross-Zagier. Their paper makes sense to me. It's concrete. Anything beyond it, I have no clue what they're talking about. So I don't know. I don't have any life solutions here. I don't know if I can get it quite the way you're going, but if I can solve my problem, maybe I'll make some money, and then I'll buy my own tenure, buy my
Right.
own university. I don't need their salaries and
Right.
little.
You'll start the Dan Rubin Technology Institute or School of Mathematics.
I know what to do. I just don't know what the world will be like, anymore.
Yeah, you could launch this online. So many people are doing these online courses. Have a good.
I am. You know what? Look, I do. Part of the. I'll just tell you. Part of the reason of doing this show was to help me. Look, I've never been on camera before. I'm trying to get more used to it, so that I thought I could be good at doing some lessons. So math for people that would help, and I may start doing some videos like that if I can think of, if I have time. But I feel like just at the time when I know how to do it, when I know what it should be, I also am beginning to think, well, what's the point of the whole enterprise? I don't know if even that track to be a mathematician. I mean, can't these mathematicians see that there's something wrong? Like when you get to the point when people are afraid, like they won't study this thing because they don't know where they're going to be, where they're going to end up. If it's not enough just to like math, just to be good at learning it. It's got to provide. I thought it would provide a kind of life for me, and now I don't know how that's going to work. And it's not just for math; it's for lots of other things too. So I don't know. I don't know what education is really going to look like anymore. But as much as I can give of the benefit of my wisdom, I guess I can try to do that. That's my plan. Do you watch? I mean, do you watch any of these math channels on YouTube?
Yeah. So my watch later list keeps getting filled up with math lectures. The IHES posts some things, Princeton, some other people. Yeah, so I continue to watch those things, which I find quite nice. And being able to do that, it's more convenient to just have that available on demand, those kinds of lectures.
But you know what? Okay, I mean, yes, it's great to have good lectures and that they're put on YouTube. I guess people are not taking advantage of this medium, right? Those are lectures meant for an audience, but in the future, people will learn. I mean, I'm thinking you should be able to use graphics, and you can talk faster. It doesn't have to be like a slide or a chalkboard talk, because we now have the benefit of video, and people can stop and go back. I don't think people have really fully utilized this medium for exposition and teaching math.
Yeah, I wonder what's going to change now, because so many schools are just doing online classes and people have had to make adjustments for that.
And you can do this better. And then they're going to realize, why do you need, a person teaching the same linear algebra, real analysis every year in every place to however many students, and probably someone has done it very well and could even do it better, and with videos that people can learn from. Now, there was all kinds of problems with grades and making sure people are doing their work. And grading work is that's the intensive part here.
Yeah.
But I don't know what it's
so
going.
Would that be the same for a mathematics class? Like just take a good mathematics class, not just like a pre-calculus kinds of thing that they should know coming into a university. But something that really requires you to dig down and understand things at like a deep level. Is that better served by having this sort of thing where you have like the best mathematician in the world who can explain it very clearly and just have that video be sent out to everyone, versus say another subject, like you have a great history professor or sociology professor that records this lecture, that you don't really get any kind of benefit of talking with your peers so much. I guess you could try to account for that. But what's the difference between mathematics and another subject in this sort of scenario. You're not just learning, these are the operations and definitions. You're learning to think mathematically about something.
Yes, I'm not ready to trade all of the college experience away. I mean, a lot of it is working long hours on these problem sets, especially having discussions and working on those problem sets with your peers, and sometimes going and talking to the professor.
Right, going to office hours, and that really contributes a lot to the experience.
Right, and of course, and there's so much else here. It's the you have to be socialized within a discipline, and you have to, absorb their norms, and you have to get to know people. I mean, so there's so many functions that higher education performs now that are purely online thing, and also the credentialing and making sure that the work has really been done and you really know.
Right.
I mean, there's so many things. So that's why I say I haven't figured this out. I don't know what it will look like in the future, but I do know what are better expositions of a subject than others.
Right.
I know how certain things should be approached, and I know how you could use video to like do it in the perfect way. Somehow, like if the graphics demonstrated the proof, right, and showed it in a way that you could, so many people are struggling to giving the same chalk talk all across the country over and over and over, and still struggling to get across something that I think someone has figured. If just one person figures out, like, here's the key idea, here's the key picture. I mean, you don't need that. I just, it's possible things will look very different in the not too distant future, and I just don't even know, because they already didn't have
less opportunity for jobs in academia after this.
Even less, because even less teaching needs to be done, and that's not good. But yeah, I don't have the answer to that, the big problem. But if people want to learn math and hear my perspective on it, on a lot of subjects, certainly all the undergraduate subjects, that's something I could do. I don't know who wants to listen to me, but it's certainly the people in my department previously did not like to listen to me, especially in other disciplines than my own. But that's something I could try to offer, try to put out there. Well, thanks so much for telling us about some number theory and career issues.
Thanks for having me on. I hope we didn't lose too many listeners and trying to go through
we always lose
some details.
Listeners are going to be lost. You understand?
Okay.
I can see now on YouTube with the analytics, like even with what few views I have, it's like they watched it for 2 seconds before dropping up. But we covered some good ground here. I'll put the timestamps, and I think people should really use this because we talked about one thing and then a totally different thing. There are some people who will love to hear us, or just me, complaining at the end, like I did. But I think also I had complaints about number theory too. So we'll see what happens. I think somewhere there's an audience for our brand of discussion. All right. Thanks so much.
All right. Thanks, Dan.
Up for now.